Okay, so in these videos, which are made mostly for me, if not entirely for me, I'm going to be going through some proofs, derivations, etc. for linear regression, logistic regression, and decision trees. These topics are all very important in applied statistics and are also apparently important in machine learning, which I will get to eventually. So we'll take it from the top. So let's have some unknown random variable y, and let's approximate it with some linear function x beta. So if the difference between what we're estimating and our estimator is simply e is equal to y minus xb. Now let's let y be some vector of unknowns. Let's let it be 1 by n in length, and let's let x be some matrix. I don't have a good way to denote that it's a matrix, but let's let it have p by 1 or p plus 1 by n elements, and let's let every first entry, every entry in the first column be 1, and the rest will be various x's. So this is x11, this is x12, dot dot dot, etc. Down here we have x and n, or sorry, xp plus 1, xp plus 1, n. And then let beta be some 1 by p plus 1 vector. So as we can see, when we multiply x by this vector by beta, such as here, we get a p plus 1 by n multiplied by a sorry, rows and columns. This is an n row p plus 1. So n by p plus 1, thought I set this up right, multiplied by p plus 1 by n, right? So we get an n by n matrix. Sorry. We get an n by 1 vector, which is what we want, because y is, of course, 1 by n. So, sorry, n by 1. So for this to make sense, that would have to be true, and it turns out it is true, as I just demonstrated. So anyway, so let's let that be some vector, right? Because it's going to be an n by 1 minus an n by 1, right? So this is a vector, this is a vector, this is a matrix, as we've seen. Anyway, so if this e vector is the difference between our y vector and this vector, then let's find some way to minimize e. And in minimizing e, we'll said more exactly, let's find a beta for which e is minimized. So a common way to do this, as many will be familiar with from the scalar version of linear regression, is to take not the minimum of e, but the minimum of e squared. So in matrix notation, we can't just take the power of this vector. Instead, what we do is we have y minus xb transpose times y minus xb, right? And it should be pretty evident that this is just equal to E transpose times E, right? You know, we can just substitute E for y minus x beta and see that that is true. And this is equal to E transpose E is equal to the sum from 1 to n of every ith E squared. You can see that's true, right? We can do a little quick demonstration to convince ourselves that this is true. So if we have, right, so E must have dimensions n by 1 because its elements here have elements n by 1. So so E transpose then is a 1 by n, so it's a 1 by n matrix, or vector I should say. And it doesn't really matter what the entries are here, but let's say E1, E2, dot, 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 En, right? And we're going to multiply E transpose by a n by 1 matrix, which is E1, E2, dot, 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 En, right? So what's going to happen? Okay, well, a simple matrix multiplication. We're going to take the element here and multiply it by the element here, and then add that to this multiplication, right? So we're going to get E1 times E1 plus E2 times E2, right, dot, 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 En times En, which is the same thing as E1 squared plus E2 squared, dot, 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 En squared, which is the same thing as the sum of EI squared 1 to the nth, right? So this is just to show that, hey, this sum of squares that we're used to from the scalar form can be written in this more general form when we have multiple betas and multiple y's and so forth. So now that we're all good on that, I'm going to clean up the board just a little bit. I'm going to need this space. So we want to minimize this thing. So we're going to take the derivative with respect to beta, because that's what we want to minimize with respect to. So if we take a derivative with respect to a certain vector, then what we have is a vector of derivatives. So this will have the length of the beta vector, so it'll be a p plus 1 length vector. And I just realized that some of this is a little fuzzy in the video. Let's see if I can improve that. Maybe some more light. I mean, it's not terrible, right? But it's not great either. Okay, well, this is a learning experience. This is probably one of the easier things to demonstrate, so hopefully it's somewhat readable. And if not, well, then I'll work on it for the future. So anyway, so this is going to be a p+1 length vector. I'm sorry, we're taking this vector, this derivative vector with respect to our matrix product here. So, which we showed is equal to this, right? So I'm going to do this in a sort of scalar proofy way. There are some matrix identities that would make this a lot faster, but I think it's illustrative to demonstrate what's going on here. So every element, so let's say every kth element of beta of this derivative vector of d beta, let's call it. Well, I've already written it up there. So every kth element of this thing up here is equal to dbk, right? This is not a vector anymore. This is a scalar. It's equal to the kth derivative, or the derivative of the kth beta of this thing. Okay, well, this is actually not so hard to see what's going on here. So if we just expand this, of the sum of, right, each EI stands for y minus x times b. And this is for a single EI, right? This isn't for the entire E vector. So a single EI must be equal to yi minus, now remember, x has both rows and columns, so it'll be a sum of xi j times beta j, and then this whole quantity squared. Right, this goes from j equals 1 to p plus 1. This goes from I equals 1 to n. How is that shown up there? Oh yeah, that's not bad. Okay. So maybe it's useful to just ask why is this true? So so for a given EI, why is EI equal to yi minus the sum of xij beta j, j equals 1, p plus 1. So remember that we had, maybe I shouldn't have erased it, but we had some y vector, y1, y2, dot, 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 yn, and we're trying to approximate it using some x vector, 1, 1, 1, 1, dot, 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 x1, 1, x2, 2, right, x, n, n, and some beta vector, which is, let's denote that, which is 1 by p plus. Okay, so what is the approximation for this y1? Well, it's going to be every element of this p plus 1 by n. We know that it's going to have a single value. It's going to be a scalar, because y1 is a scalar. And more directly, we can see that when we do this multiplication, every jth element of this vector is going to be multiplied by every but for a fixed row, every jth element in that row, where j goes from 1 to p plus 1. So that means that y1 is approximately equal to 1 times whatever, we're going to call this beta 1 for now. Hopefully that doesn't confuse us a little bit later. But right now I just mean the first element in the beta vector, which may or may not end up being called beta 1 because there's beta null, but we'll get to that. So this is approximately equal to, right, the first element in this multiplied by the first element of the first row in this matrix, which is 1, and then plus the second element here, multiplied by x11 plus, right, beta 3, oops, yeah, x12, dot, 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 dot. So maybe now we can see, I mean, this is the reason that we have p plus 1 elements and not just p elements, because this index is at beta null and this index is at 1, right? So we don't actually get to beta 1 and x1 until the second element, so maybe it's easier to just write that now so we can see what's going on there. So hopefully that wasn't too confusing. So hopefully it's clear enough now to see that, hey, this y1 is actually equal to, or approximate, right? We're approximating it by some sum of for a fixed I across all of the jth x's multiplied by the bj's, all the xj's multiplied by the bj's for a fixed I. So that's all this is. That's all that sum is. So the difference between that y that we're approximating and the thing that we're using to approximate it is just this expression here, right? And then, of course, we're going to take its square because that's what this EI is, right? So we can see how this EI is simply this, and we're taking its square value. So anyway, maybe that point was over-labored and maybe it was unnecessary, but from my own memory, it's nice to remember why these things are true. So we can take this derivative. It's pretty straightforward. This is a scalar. The derivative of a sum, I mean, this is a linear operator, so we can just move it inside. So we have the sum from I is equal to 1, and now we're going to have, I'll go ahead and write this, even though it's maybe not worth it, but you'll see what I mean. So okay, so it should be pretty easy to see that using the chain rule, we're going to first take the derivative of this quantity, right? So that's going to be 2 times yi minus, right? Everything that's inside of it stays the same. Good old chain rule. And this gets decremented down to 1, so I'll just leave that as it is. Oh, sorry, don't forget that we still have this sum out here. It's very important. And then we need to do, following with our chain rule, the derivative of what's on the inside, right? We're going to multiply that by, well, the derivative of beta k of yi, which doesn't have a beta to save its life, is just 0. minus, this is a sum. We'll just quickly, I mean, we sort of expressed it up here, and maybe I should just use that, but I'm going to go and write it here again. So this sum, right, is equal to beta null times 1 plus beta 1 times x1 plus beta 2 times x2, right, on and on and on. So for any kth beta, every term here that doesn't contain that kth beta is going to be 0 in the derivative. And whichever one does contain the kth beta is going to go to 1. And so the only thing that's going to be preserved is the x value in the sum. So, and that x value will be the jth x value because, right, we can see in this, sorry, it'll be the kth x value. Forgive me for that. I almost mixed up my indices there. Because J and K are not necessarily equal, they could be, but so this will be some xk. So we distribute this, and we also identify this as, well, that's just E, right, as we demonstrated over here, EI specifically. So I is equal to 1 to the n, 2 times EI. This is negative xk. With me so far? Now remember, this is all for the kth element of this vector. So there's going to be multiple of these. So and as we can see, we're summing from 1 to n. So that means that for this first element of a vector, this first element of a vector is minus 2 times E1 xk plus minus 2 times E2 xk, right? Right. Sorry, and this is an xk, right? I said for the kth element of the beta, the derivative with respect to beta vector. So if this is that that vector, then this is the first element of it, right? This is 1, this is 2, right down to k. Maybe this will be capital K, right? Because lowercase k is being used as an arbitrary index of its size. And we already know that its size must be equal to the same size as the original beta vector, which has p plus 1 elements. So actually this goes to p plus 1. So this is x1, this is x1, right? Everything is going to be x1 for that row. This is x2, x2, right. And then this one is going to be the p plus 1 x. I'll just write the first element of that, just so we have it there. So what we can see then is that this whole vector, building on what we know about this any given entry, can just be written as minus 2. Can this still be? Oh, you can't see that down there. Good enough. Can be written as minus 2 x transpose E vector, right? And that shouldn't take too much figuring out to see why that is. So minus 2 is a scalar. X transpose is going to be an n by p plus 1 matrix. I'm just going to erase this for a second so I have a little room. Is going to be an n by a p plus 1 multiplied by our E vector, which we decided earlier, or demonstrated earlier, I should say, is a 1 by n. Right, so this has the same number of rows as this does columns, so we're good to go. So this is equal to E1, E2, dot, 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 right? And we know that this is 1, this is, I did the transpose, so let's not get this messed up. So 1, 1, 1, 1, 1, 1, and then this must be equal to x11, x12, x13, and this is xn, xp plus 1. So the x1 is sorry, remember this was for a fixed I, as we were talking about earlier. And I is the index that goes from 1 to n. So in this case, in the transposed case, it is the columns. So the result is going to be a n by n. Right. So this whole thing can be written as minus 2 x transpose E vector. And why is that true? Well, and I didn't do a great job keeping up with these indexes. So let's just take it from the top. So, right. So this, remember, we were taking a derivative with respect um, to the inside of this, which is yi, which the derivative of that with respect to some beta k is 0, minus the sum, which is equal to, for, right, remember this is going from j is equal to 1 to p plus 1, right? So i's are fixed in this sum. So for a fixed I, we have xi 1 multiplied by beta 1. Now these are the first elements of these this matrix and this vector respectively, which doesn't actually correspond to what we're calling beta 0, right? So beta 0 here is beta 1, beta I1 is actually this 1 right here. For a given ith row, I goes from 1 to n. Hopefully that's not too confusing. So this sum is for a fixed I, and this will go to, and I've run out of room to write it. Let's write it smaller. Xi p plus 1, beta p plus 1, right? So that's why down here we get this, yeah, and this should be, let's write this a little more clearly too. So we know that our, okay, so when I left off, I was just trying to demonstrate what each element of this vector is equal to. So remember, we were taking the kth derivative of this beta vector. So we know that this derivative, this vector of derivatives, is going to have p plus 1 elements, because beta vector had p plus 1 elements. And k goes from 1 to p plus 1. So the result must be a p plus 1 to ... right? Kth element ... p plus 1, right? Where k could be 1 or 2 or anything down to p plus 1. Hopefully that's not confusing notation. So for a given k, so say we set k equal to 1, for a given k, what we have is we have the sum of pretend this is all in the first row. Maybe it'll be less confusing if I do that. We'll bring that constant out, minus 2 times the sum of ei, xi, and this is the first element, so k is equal to 1, 1. Right? Okay, so we already know that k goes from 1 to p plus 1, and I goes from 1 to n. So I've already written it down here, but we're gonna do it. So this whole thing, right, down here we have minus 2 times the sum of 1 to n of ei, xi, p plus 1, right? So this whole thing can be written as minus 2 times x transpose e vector. Why is this true? Well, minus 2 times x transpose, the multiplication of x transpose multiplied by e vector is going to give us, so e transpose is going to be an n by p plus 1. So this is going to be an n by p plus 1. and we're going to multiply that by a sorry, that's going to be a p plus 1 by n. I'm writing my rows on the right side, which is dangerous. So this is going to be a p plus 1 by n. We're going to multiply that by my e vector, which we know has n rows, so that's going to be a 1 by n, 1 by n. So, sorry, and n, I did it again, and n by 1. So we're going to end up with a p plus 1 at the end of this, which is exactly what we want. And the let's just go over the first row. So the first row is going to be whatever the first position x is for a fixed p plus 1, multiplied by the first position e, the second position x for a fixed p plus 1, multiplied by the second position e, right? So p plus 1 is indexed. In this case, it's indexed using k. So for a fixed k, we're going to have, for the first element here, of our resulting p plus 1 by 1 vector, we're going to have x fixed k 1 multiplied by beta, sorry, not by beta, by e1 plus x fixed k 2 multiplied by e2 dot 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 dot. And that's going to be true for every single row from 1 to p plus 1 of our new thing. Now this is hopefully pretty clear that this is just the same thing as we've been writing up here, right? So if we pick 1 for k, then we get the same thing we were talking about up here where we picked 1 for k, right? So that's all there is to it. So this is this. And now we can, I'm just going to clear up a little board space. Now we can finish minimizing this thing. Erase that. I can use all this bottom corner. So we need to finish minimizing this thing. So just as we often have done in the past, we're going to set it equal to 0. We're going to set it equal to 0. And first I'll note that e vector, right, we already know, is simply y vector minus x beta vector. So I'm going to go ahead and just write that here because that's the final form that we want it in. We'll see why. So we're going to set this equal to 0. So equal to 0. And we'll do some solving. So if we multiply this out, we get minus 2xt y vector minus, or I guess plus actually, huh? Plus 2xtx beta vector is equal to 0. Let's move one of these to the other side. Might as well take care of a negative, right? So we get 2xtx beta is equal to 2xty vector. We can see pretty quickly that these 2's will cancel out. And then what we're going to do is we're going to take the inverse of xtx minus 1 multiplied by xtx beta on the left, and then we have to do the same thing on the right. If we're out of space, so I'm going to go to the next line. xtx inverse multiplied by xty. So we can see that this is going to become the identity. So we get beta is equal to xtx inverse xty. And this is an estimator, so let's give it a hat. So that's how we derive the beta hat vector.